So let's go ahead and continue graphing these functions. You might remember we went ahead and listed what the parent functions were for each of these 6 functions given, and then we also recorded the transformation that has to take place. So we'll fill in this information right here after we graph the function. Okay, I think we should do this in 2 stages. Let's go ahead and graph the parent function log base 2 of x. We know 1, 0 is a point on log base 2 of x. Because log base 2 of x comes from the exponential 2 raised to the x, we know that the ordered pair 1, 2 is on the exponential. So let's switch 1, 2 and plot 2, 1. And since we also know that on the exponential 2 to the x, that the point 2, 4 is on that, we're going to graph 4, 2. Kind of a quick sketch of the parent function. And then remembering the graph continues down this way, and x equals 0 is our vertical asymptote. All right, next thing we want to do is we just want to shift these points on this graph right 3, and that will result in our graphing this equation right here. You might want to start with the vertical asymptote at x equals 0 and go ahead and move that over 3. So at x equals 3, I'm going to draw in the vertical asymptote. And then just take a couple of points on the parent function, shifting each of those right 3. So this point will move over 3. And this point also 3. Okay, and hopefully that's enough points there for us to go ahead and connect. Draw off. Now the other part of this log graph has to come down here, but it's guided by that vertical asymptote. So coming over here and listing this information, the domain of my new function, well, the domain is now 3 to infinity. The range is still all real numbers. And the equation of the vertical asymptote is x equals 3. Moving over here, we see the parent function is the same as what it was in this previous example, so we'll get that plotted pretty quickly. Remembering that we have a vertical asymptote at x equals 0 for the parent function. So now we want to move left 1 and up 4. So what's going to happen is if we move this vertical asymptote, we're going to move it left 1. We don't need to move it up 4. I mean, we could, but it's still going to be right here. So you might want to tackle the vertical asymptote first. So now let's take each of these points, some of these key points, and move them left 1 and up 4. So this point will come over here, up 4. Go back to this color. So this point corresponds with this point. So I know that this part of the graph is going to be drawn down like this. So now this ordered pair right here, left 1, up 4, it's right here. And lastly, this point. So now we can complete the log graph. Okay, filling in this information, the domain for this new graph is going to be -1 to infinity. The range is still all real numbers, and the equation of the vertical asymptote is x equals -1. All right, for these next 2 functions right here, the parent function is for both of them, it is log base 10 of x. So for a log function, we know we're going to pass through 1, 0. Remembering that this log function comes from the inverse of 10 to the x. If x is 1, then the output would be 10. So instead of using the point 110, we're going to use 10, 1. So 10, 1 is going to be about right here, which makes sense because that bigger base tells us that we're closer to the positive x-axis. And then drawing downward this way. Remembering that the equation of the vertical asymptote for log base 10 is x equals 0. Okay. So now we're coming over here, and the transformation is let's reflect this graph through the x-axis. So we want to create a mirror image. So I'm probably just going to start with 0, 1, and then this point over here, which is 10, 1, becomes 10, negative 1. So trying to create a mirror image through the x-axis. So these two certainly look like I could reflect across the x-axis and they'd coincide. Now this part of the graph right here is just going to be coming upward like this. So the domain didn't change. Doesn't look like the range changed from the parent function. And it looks like I still have the same vertical asymptote. Let's quickly get this parent function on, the same as it was in the previous problem. The transformation tells us we're going to do a reflection through the y-axis, so we need a mirror image across the y-axis. So this point at 1, 0 is going to be reflected over here to negative 1, 0. The x's change, they're opposites. The y's stay the same. So this point right here at 10, positive 1 becomes negative 10 over here, positive 1. Connecting, drawing downward. Looks like a mirror image across the y-axis, which it should be. Let's look at the domain for my new graph. It's negative infinity and it stops at 0. Right before 0. The range is still all real numbers. And we still have the same vertical asymptote at x equals 0. Okay, for the last two, both of these have the same parent function. It's the natural log graph. So we'll get started with the natural log graph. Still passes through 1, 0, but you might remember that the log function with base e comes from e to the x. So if we're using e to the x and x is 1, then the answer is going to be 2.72. So I switch those ordered pairs and I go to 2.72 as the x and up to 1. And I think if you look back at the notes from the other page, that this other point was a little bit past 7 up at 2. So this is the natural log graph. And of course it's right above us too at the very top of this paper. All right, the transformations tell us that we're going to, reflect through the x-axis. I would do that first, and then I'm going to move it up 2. You can do this in 2 stages if you want. I might lightly in a pencil do the reflection through the x-axis first, and then the final graph will be in blue, and it'll be shifted to up 2. So I'm going to reflect through the x-axis, so that's going to be across this way. So this point will come down here. And this point will be down here. So I'm going to kind of lightly draw in pencil the reflection through the x-axis. But then in blue, I'm going to take all these points and shift them up 2. So this point is still on the reflection, so shifting it up 2. This point right here, shifting it up 2. Well, that's not going to be right. 1, 2 would be right here, actually. And then this point shifted up 2 would fall on the x-axis. So I'm going to connect these points, draw the graph off. But then over here, I'm still going to be guided by the vertical asymptote at x equals 0. All right, so the domain is 0 to infinity. The range is all real numbers. And the equation of the vertical asymptote is still x equals 0. Okay, and I'm going to leave this one for you. It'll be posted on the key as well, but we can see that it's just the same parent function of the natural log graph, and then we're going to actually shift all the points left 2. So when you kind of think about that, when you shift the points left 2, your vertical asymptote's also going to change. So just kind of attempt that one on your own and then consult the key just to kind of self-assess and make sure you're on the right track there. All right, so we have more objectives, okay, and so on this page right here, this next objective, let me see, take this down a little bit, is to change from one form to another, meaning change from either the log form to exponential or change from an exponential to a log form. So this box is kind of important. It says that y equals log base b of x if and only if b to the y equals x. And that's kind of going back to what I did on that first page when we were talking about, okay, different names for the same graph. So we're just going to change forms. It's kind of like if you think about, you know, 1/2, the fraction. If I didn't want a fraction, I could change it to a decimal. I could change it to 0.5. So they represent the same value. It's just that they're in a different form. Well, that's what this is saying right here. Okay, so it's saying if I could either write a log in this form or I could write a log as an exponential in this form, and these two are equivalent. So what's happening here when you're asked to change from log to exponential is, if you think about it, some people call it around the world. If you're going to go to an exponential, the good place to start may be at the base, because you need a base on an exponential. And so I've heard some others say, hey, let's just go around the world with changing this form from log to exponential. And they mean start at the base, come around here, pick up y as an exponent. So we've got b raised to the y, and then it's equal to the argument, or x. So that's what we're going to do here with these 6 examples. You're going to have a couple problems that ask you to change from log form to exponential form. So kind of think about around the world. It might be a little trick, but you know, it might help. So if this is a log function right here, then the base on the log is 7, so it has to be the base on the exponential. So 7 raised to what power? Around the world to the 3rd power, and that's equal to x. We're not asked to solve this. The objective is just to change forms, and that's it. So for this log equation, let's change it to an exponential equation. 5 squared equals 25. We know that to be true, so all should be good. Let's move on. Okay, now over here, we're going to go this way. 4 raised to the y equals, because you're going across the equal sign, 4 raised to the y equals 26. Okay. If you want to stop right now and kind of self-assess and see if you can do those and then start it again, the video, just to make sure that you're on the right track, that'd probably be a good idea. This one, we're going to come this way across the equal sign. So done, we changed from log to exponential form. Well, if we went that way, we got to go the other way. This says let's take exponentials and rewrite them as logs. None of these equations right here have a log in them, so that's what our objective is to change from exponential to logs. So there's a couple ways to do this, but what I might do is I might start with the exponent, y, like I did over here. Y equals, go to the exponent and set it equal to, then insert log with this base, and then with this argument right here. So for example, I would start here and say, this is 5 equals, the exponent equals, always do log. The base on the exponential is 2, so it has to be a little subscript here. And then you're going to have x. And notice that this drops down a little bit. It's a subscript. It's not on the same line. Okay, here's another example. What should we do to change it to log? I would start with the exponent. 3 equals log base b of the argument 27. You can always check your work by doing what we did up here to go back to the exponential form. You can check it by doing around the world. So you can go the base here, b to the 3rd power equals 27, and that's what we started with. Okay, here, this is the exponent. Doesn't matter what it is, y, x, r. There's 26 letters of the alphabet. You know, they could have used any of those letters to represent the exponent. So y equals log base e of 33. And that's a great answer. Another form of that is, if you notice log base e, that could be rewritten as ln, natural log 33. So either one of those are correct. Notice there's only one equal sign. There's not another equal sign here. parentheses aren't necessary, but sometimes it just kind of cleans it up. Okay, notice we don't have an exponent here, but I can rewrite this as an exponent. This is the cube root of 64. This can be rewritten before we need to do what we need to do here. This can be rewritten as 64 raised to the 1/3 power. If we had the square root of 64, then that could be rewritten as 64 raised to the 1/2 power, because this is an understood root of 2. If we had the 4th root of 64, this is going to be rewritten as 64 raised to the 1/4 power. So in order to accomplish these objectives, this objective right here, changing to a log form, we need an exponent. So this can be rewritten as 64 raised to the 1/3 power equals 4. And now we can accomplish our objective. So start with the exponent, 1/3 equals log, throw the log in there, the base is 64, and then the 4 is the argument. So this objective up here, these objectives up here is just changing from one form to the other, not solving or anything, just making a problem look a little bit different. Give it a different name, if you will, okay? All right, we got a lot of problems down here, and it's the same objective. The objective is evaluate, and that usually means find an answer. We're going to do all these by hand, but we can do them on a calculator. And just to say this, you guys are going to have a scientific calculator. So when I'm done doing a few of these and you get the hang of what we're doing by hand, I'll show you on the calculator how you can actually go through and find the answer as well. But it's good to know how these answers are found without a calculator. Okay, what this is saying to us is log base 6 of 36. It has an answer. It has a numerical value. So if you think about these log problems down here, it might be easier to change them to exponentials and then solve. So what we do is we think about this for a minute. We go, you know what, we want to find what this answer is. So we just kind of think, okay, well, this is equal to what number x? What is the answer x for this problem? Notice I just created an equation like what we had up here, an equation. Let's change this equation, this log equation, to an exponential equation by going around the world. So this is saying 6 to the x is equal to 36. Well, I think intuitively we know that the exponent is 2. So if I come over here and said x equals 2, I could be finished. I'm done. But to get ready for some of these other problems over here where it won't be so intuitive, here's the strategy we use to get to as well. Okay, when I look at this equation right here, I see a base of 6 and I see a number of 36. Let me rewrite the larger number, if I can, as a power of this other base. So I'm just going to bring down 6 to the x, and I'm going to say 36 is rewritten as 6 squared. Well, if we have an equality here and I have the same base, well, the bases kind of fall out, and I say, well, if the bases are the same, then the exponents have to be the same. We do what we call equate the exponents once we have the same base. All right? 5 raised to what power is 125? That's how this is read. Well, you might think, well, I think that answer's 3, and it is, but how do we show the work that supports that? Well, think about this as being equal to some number, some answer that I'm trying to find. I just created an equation where I can change this log equation to an exponential. 5 raised to what power x would equal 125? Well, if I don't have a calculator, I might think, well, let me take the larger of the two numbers, 5 and 125, and rewrite 125 as a power of 5. Well, 5 to the 3rd power is 125. Once you have the same bases, then your exponents can be equated, equal to each other. So the answer here for this problem is x equals 3. All right, let's set this equal to x, change to 36 to the x equals 6. But notice now how the slight change from the first problem we did is that this base is 36. This is the bigger number. I want to rewrite 36 as the power of the smaller number. So 36 again is 6 squared, but that doesn't mean that the x went away. I'm going to put the x up here because this is 36 equals 6. Now this 6 has an understood exponent of 1. All right, when I look at this right here, I can multiply these two exponents together because we have a property of exponents that say, hey, you can multiply these. So I've got the base of 6 raised to the 2x power equals 6 to the 1st. I'm going to come over here. I have the same bases, so let's equate the exponents 2x has to equal that 1. These two have to be equal. Now I have an algebraic equation where I divide both sides by 2 to get x by itself, and I'm going to get my answer. So my answer here is x equals 1/2. So let's just think about that for just a second. If x is 1/2, it's saying that 36 raised to the 1/2 power is equal to 6. A 1/2 power is the same thing as the square root, like was mentioned up here. So think about what the square root of 36 is. Well, it is 6. So I feel like I got the right answer. Okay, let's come down here and look at some fractions. Same thing, 6 raised to what power is 1 over 36. A little bit different than 36 here. This is 1 over 36. But if we follow the plan, the strategy, okay, we should be able to get it to work out. 6 to the x equals this fraction. What I might want to do is rewrite the 36 as it stands in the denominator as 6 squared. So it's still 1 over 6 squared. Okay, I can't drop out the bases because this 6 is in the denominator of a fraction. I have one more step. So bring down 6 to the x. What do we want to do if we want to bring 6 up to the numerator? Well, we adjust that exponent to a negative number. So we used to do it the other way. We used to take and make a positive exponent by dropping the 6 to the denominator and adjusting the exponent to positive. Now these bases are the same, so my answer is going to just be x equals -2. And hopefully that kind of makes sense to you that 6 raised to the -2 power would give us 1 over 36, a very small number. Same thing's going to happen here. My key shows the work. Okay, let's come over here to this problem. 8 raised to what power is a smaller answer of 2? So let this equal x. Okay, the bigger number is 8. Let's see if we can rewrite it 8 as a power of 2. And it can be. 8 can be rewritten as 2 to the 3rd power. And then you still have an x here. And don't forget that 2 has an understood exponent of 1. So this problem becomes very similar to this one. Multiply the exponents together. 2 to the 3x, so you can get rid of parentheses, equals 2 to the 1st. I have the same bases, so 3x equals 1, an algebraic equation. Divide both sides by 3, so x is 1/3. So if we go back and try to check it in the original exponential equation, 8 to the 1/3 power means the cube root of 8, and definitely the cube root of 8 is equal to the value of 2. So it all does check. All right, coming down here, I'm going to skip these two for just a second, come down to this one. This says 6 raised to what power x is equal to 1. Well, there's just not a lot I can do with this other than use my reasoning skills. What's the only way you're going to get an answer 1? What does your exponent have to be? So we should kind of know that that is going to be x equals 0. Anything to the 0 power gives us 1. I'm going to come over here to this first one because it looks a little different. This is kind of similar to some of the other ones that we've done. That'll be on the key. So let's look at what's going on here. So 6 raised to what power is equal to the square root of 6? I don't need 6 underneath the square root, so let's rewrite this. 6 to the x comes down. Square root of 6 can be rewritten as 6 to the 1/2 power. Done. Same basis. The exponents have to be equal. So the takeaway here is that any square roots like this in this objective probably need to be rewritten as a 1/2 power. Okay, let's come down here to this one. 8 raised to the x power is equal to 1 over the square root of 8. I got a couple things going on. I got a fraction, which I don't want. I want the 8 to come up top, but I don't want that square root there. So let's bring 8 to the x down. Let's rewrite the denominator as 8 to the 1/2 power. That's what square root means, with a fractional exponent. Now I can bring 8 out of the denominator, and when I bring it up to the numerator, I adjust the exponent to -1/2. Same bases now, and I have my answer because the exponents have to be equal. Okay, this one looks a little different. 4 raised to the x equals all of this, 4 to the 6th. So the bases are the same. My answer is just 6. Okay, you might see that this is kind of a special kind of situation. We have a log function with the base 4, and then inside that we have an exponential with the base 4. So just kind of think about those two undoing each other, a log and an exponential, and your answer is going to be what the exponent was here. So if that exponent was 7, your answer would be 7 if everything else stayed the same. Okay, do this last one. Okay. The bigger number here that I see is 9, but I can rewrite 9 as 3 squared. So keep the fraction, 1 over 3 squared. Bring the 3 up out of the denominator, adjusting the exponent to negative, and our answer is going to be -2. So 3 raised to the -2 power would result in 1 over 9. Okay. All right. And last objective. Move this down a little bit. Okay, we've got some properties of logs. Okay, this just says that log base b of b equals 1 because b to the 1 equals b. Well, we did a problem like this. I think, maybe we did it on the other side. Let me give you a quick example. Log base 7 of 7. So these two b values are the same. If I wanted to find this value, I'd set it equal to x. Well, 7 to what power is 7? Well, the only answer would be to the first power. So this could be rewritten as 7 to the x equals 7. Same bases. Because we have an understood exponent of 1 here, we know the answer is 1. That's all that property is saying. This is one we did on the other side, where if you take a base and you raise it to a power, and you want an answer of 1, then the answer should be 0. So any number raised to the 0 should be 1. Okay. Then we also have the inverse property here. Okay, if we define f of x to be a log function, but g of x another function to be the exponential function that has the same base here as is in the log, and it tells us further that f and g are inverse functions, then from our past studies, we know that when we do two compositions for inverse functions, when we put g inside of f and f inside of g and do all the simplification, the answer should work out to be x. So it's saying here, if you do the composition of f of g of x, so g is up here, put b of x in for the x here, we're going to get log b, and then put b of x in for this x, we get b to the x. Well, this is what we did on the other side too. This is a log function with the base b with an exponential function with the base b. Our answer should be x. Then we also have to consider what happens when we put the f function up here inside the g function. So wherever you see x up here, you're going to plug in log base b of x. Same thing here. You have an exponential with base b raised to a power with the log base b. Those two undo each other. Your answer is x. So it says use the properties that we just saw to evaluate or simplify. So hopefully you're kind of thinking ahead going, log base 7, exponential 7, my answer should be 8. Exponential base 5, log base 5, my answer should be 17. Exponential base 2, log base 2, my answer should be x. All right, this further talks about the common log, which I mentioned, base 10, and the natural log, base e, which can also be written like this. Okay, and we have more properties here. But down here with these, let's just go ahead and see if we can kind of evaluate them based on what we've seen so far. Okay, so for this one, log of 1,000 without a calculator. If you put the understood base of 10, I could do what I did on the other side, okay, when I evaluated, and go, okay, 10 raised to what power is 1,000? 1,000's the bigger number. Yes, it can be rewritten as a power of 10. So 1,000 comes from 10 cubed. The bases are the same. My answer is 3. Okay, looking at this example, I see a base 10 exponential and I see an exponent with the log with base 10 that's not written in. So I know these two undo each other, so my answer should be just the square root of x. That was from the top of the page when we looked at inverse functions. Okay, all right, looking at this, this is a log base 10 with an exponential base 10, so my answer should be 8. right here, sometimes it's helpful to rewrite ln as log base e, and then continue with the rest of the problem, e to the 9x. Well, log base e with an exponential e, those undo each other, they're inverses. My answer is just going to be 9x. Okay, here, e raised to a ln, you could rewrite that as e raised to the log base e, replace ln with log base e, and then carry on with 7x squared. So base e with an exponential, base e with a log, undo each other. Your answer should just be 7x squared. Here, ln, I feel more comfortable rewriting ln as log base e. So ln rewrites as log base e, don't forget the e. Now remember, there's an understood exponent of 1 here. So log base e, exponential e, undo each other. My answer is 1. Okay, here, e, ln is translated to log base e. Don't forget the 300. Base e, log base e. Answer, 300. ln is log base e. Don't forget the e to the 9th. These two undo each other. Inverse operations, we're at 9. Now this one, if you said 7, is going to be incorrect because we have to bring e out of the denominator. So 2 things here. Change ln to log base e. Then go ahead and tackle this, rewriting this as e raised to the negative 7. Now we can undo these 2 inverse operations, and my answer is negative 7. Okay. On the calculator, all of these can be done. It's just a matter of finding the correct keystrokes. Okay, so if I wanted to take log of 10 raised to the 8th, your log key is right here, your ln key is right here. So if I wanted to do this problem log, okay, let's see. You know, I'm going to save this for another time. I might make another video. I'm running out of time here. I might make another video to show you how to do that. Otherwise, remember YouTube. You know, type in your model on your calculator and ask it how to compute some of these. But I'll probably create another video just doing calculator keystrokes for these types of problems.